Ever crossed the majestic London Tower Bridge and wondered about those high walkways connecting the two towers? They seem like the perfect spot for a scenic stroll, right? But here's the twist. They're almost never used for their original purpose. So, what if they were never built at all? Would the bridge still function? Today, we're diving deep into the heart of this iconic landmark to uncover the secrets hidden within its engine rooms and find out what truly makes this Victorian marvel tick. Tower Bridge is a global icon, a symbol of London instantly recognized around the world. Every year, it opens its mighty arms, or bascules, about 800 times to let tall ships pass through on the River Thames. It's a spectacular sight, a perfect blend of engineering and artistry. But the real magic isn't just in the grand opening. It's in the complex, powerful machinery hidden from public view. To understand the bridge, we need to go behind the scenes, into the Victorian engine rooms, and explore the ingenious technology that has kept it moving for over a century. Let's travel back to the late 19th century. London was a bustling port, and the demand for a new bridge downstream from London Bridge was immense. But there was a problem. A traditional bridge would block the vital river traffic to the Pool of London docks. The solution was a bascule bridge, a design that could open for ships. The chief architect, Sir Horace Jones, and the engineer, Sir John Wolfe Barry, were tasked with this monumental project. They envisioned a bridge that was not only functional but also aesthetically pleasing, seamlessly blending with the nearby Tower of London. And so, the magnificent Gothic-style towers we see today were born. The initial plan seemed straightforward. Two giant leaves, hinged at the bases, would lift up. Simple, right? Not quite. When the engineers started crunching the numbers, they hit a massive snag. Each bascule weighed over 1,000 tons. Lifting that much dead weight directly would require an astronomical amount of power, far beyond what was practical at the time. The whole project was on the verge of being an impossible dream. The bridge was simply too heavy to lift efficiently. This is where the real genius of Tower Bridge's design comes into play. To solve the weight problem, the engineers came up with a brilliant solution: a counterweight. Think of it like a seesaw. If you have a heavy person on one end, you need an equally heavy person on the other to balance it out. The same principle applies here. A massive counterweight, weighing just as much as the bascule itself, was attached to the other end of the pivot. This meant that the engine didn't have to lift the full 1,000 tons. Instead, it only needed to provide enough force to overcome friction and inertia, to gently tip the perfectly balanced scale. But adding this enormous counterweight created a new, equally massive problem. When the bridge opens, the bascule pivots upwards. At the same time, the counterweight on the other end of the lever swings downwards, deep into the foundations of the bridge. The original foundation designs didn't account for this. There was simply no space for these gigantic metal boxes to move. The engineers had to go back to the drawing board and completely redesign the bridge's piers. They had to excavate huge empty chambers beneath the river level inside each pier. These cavernous spaces are the hidden secret that allows the counterweights to swing freely, enabling the bridge to rise. Without these chambers, the counterweights would have just crashed into solid concrete, and the bridge would have been immovable. So, we have a balanced system. But how is that initial push, that crucial nudge to get things moving, actually generated? This is where we enter the original engine rooms. Forget modern electric motors. This was the age of steam and water. The power source was a hydraulic system. Giant steam engines would pump water into enormous containers called hydraulic accumulators. These accumulators stored water under immense pressure, around 750 pounds per square inch. This high-pressure water was essentially power on tap, ready to be released whenever the bridge needed to open. When the bridge master gave the signal, a series of valves would open, releasing this pressurized water. The water would flow through a network of pipes to the heart of the lifting mechanism, the hydraulic motors. Now, these aren't motors in the way we think of them today. They are powerful engines that convert the pressure of the water into rotational motion. Imagine 3 pistons arranged around a central crankshaft. As high-pressure water is forced into one cylinder, it pushes a piston, which turns the shaft. The system is designed so that as one piston finishes its stroke, the next one takes over, creating a smooth, continuous rotation. But even with this powerful hydraulic motor, there's still a final step. The rotation of the motor needs to be translated into the massive force required to lift the bascule. This is achieved through a classic piece of engineering, a gear system. The hydraulic motor turns a small gear, called a pinion. This pinion meshes with a much larger curved gear segment, known as a rack, which is fixed to the bascule itself. This is where torque multiplication happens. Because the pinion is so much smaller than the rack, one rotation of the pinion only moves the rack a very small distance. This gearing system dramatically multiplies the force, or torque, generated by the hydraulic motor. It's like using a long wrench to loosen a tight bolt. The small effort you apply at the end of the handle is magnified into a powerful turning force at the bolt. In the same way, the relatively gentle turning of the hydraulic motor is transformed into an immense, unstoppable force capable of lifting a 1,000-ton bridge leaf against the wind and friction. So, the pinion gear slowly crawls along the teeth of the giant rack, and with majestic grace, the bascule begins its ascent, opening the gateway to the city. The entire process, from the steam engines pressurizing the water to the final gear turning, is a symphony of Victorian engineering, a testament to the ingenuity and problem-solving skills of its creators. Now, let's go back to our original question. What about those high-level walkways? They were included in the original design so that pedestrians could still cross the river even when the bridge was open for ships. It was a thoughtful idea, but in practice, it didn't quite work out. People preferred to wait and watch the spectacle of the bridge opening rather than climb all those stairs. By 1910, the walkways were closed to the public due to infrequent use. So, what if they were never built? Would the bridge still work? Absolutely. The walkways are structurally independent of the lifting mechanism. They are essentially a separate, static bridge suspended between the two towers. The core functionality, the bascules, the counterweights, the hydraulic system, and the gearing is all contained within the piers and the base of the bridge. The walkways were an accessory, not a necessity for the bridge's operation. Removing them from the original design would have saved some money and weight. But the fundamental engineering principles that make the bridge lift would have remained exactly the same. Today, while the original steam engines are no longer in primary use, they were replaced with a more efficient electro-hydraulic system in the 1970s. The fundamental principles of counterweights and hydraulic power remain. The Victorian engine rooms are preserved as a museum, a fascinating glimpse into the past. And those high-level walkways, they were reopened in 1982 as part of the TowerBridge exhibition, now featuring a spectacular glass floor that offers a dizzying, bird's-eye view of the traffic and river below. They finally found their true calling, not as a mundane pedestrian crossing, but as a unique and thrilling viewpoint. The story of TowerBridge is a story of overcoming immense challenges with brilliant solutions. It teaches us that sometimes, the most important parts of a structure are the ones you can't see: the hidden chambers, the balanced counterweights, and the powerful, intricate machinery working in perfect harmony. It stands as a powerful reminder that even the grandest visions are built upon a foundation of clever engineering and relentless problem-solving. Thanks so much for joining us on this engineering adventure into the heart of London's Tower Bridge. If you enjoyed this deep dive, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you won't miss our next exploration. See you in the next video.